Good morning everyone. Welcome you all to the fifth session of Special Theory of Relativity of 5th semester of Physics. I am Sunil MH, Assistant Professor of Physics in Government First Grade College, Ranebennur. Here, in this session, we are going to study the two major concepts of Special Theory of Relativity are length contraction and time dilation, which were derived using Lorentz transformation equation. The length contraction is also called Lorentz-Fitzgerald contraction. He is a man whose name is Fitzgerald. With collaboration of Lorentz, he determined this thing. The things which we require before going to this session are frames of references, dynamics of the system, Lorentz transformation equation, which we were studied in the last session. The Lorentz-Fitzgerald contraction, or simply it is called as length contraction. Let us consider two frames of references S and S prime. S prime frame is moving with the velocity v with respect to S frame, which is at a distance of Vt from S frame. Let us take a rod of ends A and B. A and B are the ends of the rod with respect to S prime frame. Here, the two frames are coincide at t is equal to 0. When the time t is equal to 0, the two origins O and O prime are coinciding each other. S prime frame moves with the velocity v with respect to S frame along the x-axis. We are considering the direction of S prime frame, or we are considering S prime frame is moving along the x-axis only. There is no motion along y and z axis. The rod AB is at rest with respect to S prime frame. The rod AB is taken at rest with respect to S frame of reference. The coordinates of point A, this point A, with respect to S and S prime frames are taken as x1 and x1 prime. That is, it is at the coordinate x1 comma x1 prime with respect to S and S prime frames. Similarly, the coordinates of this point B with respect to S and S prime frame respectively x2 and x2 prime. x2 belongs to S frame and x2 prime belongs to S prime frame. Here, the length of the rod AB with respect to S frame is x2 minus x1. This coordinate x2 minus x1, and the length of the rod with respect to S prime frame, which is at rest with respect to that frame, is x2 prime minus x1 prime. So look at this picture here. A particle, or it is a sphere which is at rest v is equal to 0. When it moves with the velocity 0.3 times of velocity of light, somewhat it is contrasted. When it is moving with 0.6 times of velocity of light, it is further contrasting. And when we increase its speed, that is v is equal to 0.9, say, it's almost contrasted. Look at the difference between the sphere and the here it seems to be like a ellipsoid. So we are going to derive the length contraction equation here. The length of the rod with respect to S prime frame, that is x2 prime minus x1 prime, is called as proper length of the rod. It is indicated by L0 is equal to x2 prime minus x1 prime. Similarly, length of the rod with respect to S prime frame is called as improper length, which is given by L is equal to x2 minus x1. According to Lorentz transformation equation, we can write Lorentz transform equation for coordinates. We can write x2 prime is equal to x2 minus vt by square root of 1 minus v square by c square, and x1 prime is equal to x1 minus vt by square root of 1 minus v square by c square. Subtracting these equation and simplifying, that is subtract x2 prime minus x1 prime, we get x2 minus x1 divided by root of 1 minus v square by c square. We have mentioned that x2 prime minus x1 prime is equal to L naught and x2 minus x1 as improper length L. So we can write L is equal to L naught into square root of 1 minus v square by c square. By looking at this equation, L seems to be lesser than L naught. This phenomena is called as Lorentz-Fitzgerald contraction. Contraction is appreciable only if that rod is moving with the velocity nearly equal to the velocity of light. It means the length of the rod seems to be contrasted, means its length seems to be decreased for a frame of reference which is moving nearly with the velocity of the light. So look at this picture. Here we have a rod, a square and a circle which are in a reference frame which is at rest. For a frame of reference which is in motion, nearly its velocity is equal to the velocity of light. Look at the length here, this much, and look at this length here. It seems to be contrasted. Here the square, the size of the square is decreased, and the circle seems to be ellipsoid. So this is an example how length contraction taken place in frames of references. The second important thing in the special theory of relativity is time dilation. Look at this diagram. Here we have two frames, S and S prime frame, which is moving with the velocity v. Here consider 2 points A and B where the two separate events taking place. The two separate events taking place at A and B. The first event measured by the clock which is at rest with respect to S prime is T1 prime, and the event recorded by this clock taken place at B is T2 prime, where T1 and T2 are the time recorded by the observer who is at S frame of same events. Here the two frames are coinciding at t is equal to 0. S prime frame is moving with the velocity v with respect to S frame along the x-axis. We are seeing that the particle or the frame S prime is moving along the x-axis only. There is no displacement along y and z-axis. Two events taking with respect to the clock measured by the S prime frame which is at rest with respect to that S prime frame are T1 prime and T2 prime. The same events are as measured by the clock in S frame are T1 and T2. The time measured by the observer in the S prime which is moving with the velocity v with respect to S prime frame are T1 and T2. So when we subtract the time between those two events, we get a time interval between the two events. Let T0 is equal to T2 prime minus T1 prime is called the proper time interval measured by the clock S prime frame which is at rest with respect to S prime frame, and T is equal to T2 minus T1 is the time interval measured by the clock in the S frame. So look at this example here. The two persons are twin sisters are on the earth. One is moving in a rocket which is almost going with the speed of light. Another left on the earth. Here they have started at the same time after a lapse of years or a lapse of time, the clock on the earth measuring a longer time than the clock on the rocket measuring a lesser time. This says that this is an example to say time dilation. Let us derive this time dilation equation. From Lorentz transformation equation, we can write T1, that is time recorded by the observer in S prime frame. T1 is equal to T1 prime plus Vx prime by c square divided by square root of 1 minus v square by c square, and T2 is equal to T2 prime plus Vx prime by c square divided by square root of 1 minus v square by c square. Subtracting these two equations, that is T1 from T2, T2 minus T1 is equal to T2 prime minus T1 prime divided by square root of 1 minus v square by c square. Already it is mentioned that T2 minus T1 is equal to time t, that is the time interval between the two events observed or recorded by the observer in S frame, that is improper time interval, and T0 is the time interval measured by the observer in the S prime frame, in which the clock is at rest with respect to that frame of reference, is given by T is equal to T0 by square root of 1 minus v square by c square. From this we can see that T is greater than T0, that is the time measured by the clock which is moving with respect to another frame measuring a larger time than the clock which is at rest with respect to that frame of reference. That is, stationary clock measures a longer time interval between the two events occurring in a moving frame of reference than does a clock in a moving frame. This phenomena is called as time dilation. Look at this example. A stationary clock measuring two clocks in some frame. One is moving with a 87% speed of light and another is at rest, which is measuring some larger time than the moving clock. Also we can see that this clock is contrasted. Example for length contraction. Here the time delayed and the length contraction. This is an application of time dilation phenomena, that is called the twin paradox. So look at this picture. A man and a girl is on the earth. The girl started to move in a spaceship or a rocket at some time. So look at this clock here and here. They are started at the same time. This lady has started the journey at the same time. When she came back after a lapse of time, there was a greater time was taken in Earth. Then that in this rocket, the time lapse or the time taken is smaller. This is an example for time dilation. The clock in a moving frame goes slower than the clock on the surface of the earth. Out of the two twin brothers, who is stayed on the earth and one who goes beyond the earth for the journey with the speed of light. One who goes into the space seems to be younger. He seems to be younger than his brother who stayed behind on the earth, in accordance with T is equal to T0 by square root of 1 minus V square by C square. With reference to time dilation, the person or the brother who stayed on the earth become older than the brother who went for a journey in a spaceship nearly equal to the velocity of light. This phenomena is called as twin paradox. So let us see some problems in this session. Consider a rod of 1.5 meter long is moving along its length with a velocity of 0.5 c, that is 0.5 times the velocity of light. Calculate its length as it appears to an observer on the earth. B. Moving with the rod itself. So what are the things given? That is L naught. That is a proper length of the rod which is measured by the observer at rest with respect to that rod. That is 1.5 meter. The velocity of that frame of reference is 0.5 c, and we need to calculate L. So from the length contraction equation, the rod to the observer on the earth is given by L is equal to L naught into square root of 1 minus V square by C square. Substituting the values of C, V and L naught, we get 1.299 meters. Yes, look at this. Here the original length, the proper length is 1.5 meter, and the calculated length for the observer who is moving with some velocity is 1.29, nearly 1.3. That seems to be contracted. The length has decreased. For an observer, moving with the rod itself is 1.5 meter because he is at rest with respect to that frame or with respect to that rod. So he himself find its length is equal to 1.5 meter. Next problem, a particle with a proper lifetime of 2 microseconds moves through the laboratory at 2.5 into 10 to the power of plus 8 meter per second. Find out A. What is its lifetime as measured by the observer in the laboratory. B. What will be the distance traversed before disintegration. Solution. Given things are T naught, that is proper time interval is 2 microsecond. V. Velocity of that frame of reference 2.5 into 10 to the power of plus 8 meter per second, and we need to calculate time, that is the lifetime measured by the observer on the laboratory. From the time dilation equation, we can write T is equal to T naught by square root of 1 minus V square by C square. Substituting T naught as 2 microsecond, V is 2.5 into 10 power plus 8 and C is 3 into 10 power plus 8. Substituting these values and calculating, we get T is equal to 3.6 into 10 to the power of minus 6. Look at these two things. Here it is the proper time interval is 2 microsecond, and the improper time interval, that is longer time duration 3.6 microsecond. This seems to be increased. The time is increased, or we can say time has delayed. The second thing, B, we need to find the distance traversed by the particle before disintegration. The average distance traveled by the particle before disintegration is equal to the velocity and the time. Velocity, if when we multiply velocity with time, we get the distance, and that is the velocity is given 2.8 into 10 power plus 8 meter per second, and we have found the time is 3.6 microsecond. Substituting this value and calculating, we get 900 meters. So the things which we studied in this session are Lorentz-Fitzgerald or length contraction, time dilation, twin paradox, and some of the problems on length contraction and time dilation. These are some of the references books you can go through this to study special theory of relativity. With this, I put an end to this session. Thank you, one and all.